Hey guys, it's Mr. Weaver. I can't be with you today, so I made this video for you. First, quick review. The three causes of ocean surface currents, we've already reviewed these, was the Coriolis effect, whirlwind belts, and continental deflection. Today, I would like to go over how large bodies of water can influence weather and climate, especially when we're talking about currents. So we'll skip through this information we've already covered, and I want to go here to the Gulf Stream. I know we've talked about the Gulf Stream already, but I'd like to talk a little bit more about it. Okay, we know it's an ocean current. We know it's the one that makes Florida warm because it brings up warm water from the equator, and as the wind blows across this warm water, it warms the air, then the air warms the land. That's why California is cold, because it has a cold water current that runs past it, and Florida is warm. We also talked about how it moves towards Europe this way, and it actually makes England warmer than it should be. So, if we look up here, the Gulf Stream is an ocean current that carries warm water from just north of the equator by the Atlantic coast of North America and across the Atlantic towards Europe. And I've got a couple of places I want to go to. Okay, this one's actually pretty good. I like it because it shows the temperatures. So here's the typical temperatures, and over here is London, and you can see it's in this shade of blue down here where it's a little bit warmer. And if we look at St. John's, which is about on the same latitude, it's much colder. We put the Gulf Stream in action, you can see that that warm water is pushing up this way, and that's what's warming England. I like this graphic because it shows how the Gulf Stream actually comes here and warms Iceland. Iceland you always think of as a cold, wintry place, but actually it's not as bad as people think. If we go here, this shows the average temperatures in Iceland different times of the year. If you look in July, it can get up to 57 degrees Fahrenheit. And also, like right about now in February, their temperature is comparable to ours. They're right below 30 degrees, so they're a little bit colder than we are, but not by much. I'd also like to talk about El Nino, another type of current. El Nino is an ocean current that occurs on a 5-year cycle. The trade winds here will blow in this direction. As they do, they push back the warm water that's on the surface. And it's kind of like when you blow on soup. It makes that little dimple in it. That's what happens. As the water gets blown back this way, it actually builds up out here in the Atlantic a big bubble of warm water. Now, don't picture like a big hump or hill of water out in the middle of the Pacific. It's actually only an inch or two tall, but it's bigger than all of the United States put together. What will happen then is for 5 years the wind blows really hard in that direction, and on the 5th year so much water is pushed back that the wind can't hold it any longer, and all that warm water rolls back towards the United States. When it does, we get a lot of rains and flooding, and sometimes we get a lot of record snow. So if we go here, we can actually view El Nino right here. If you look right here, the wind's blowing back the warm water this way. Then all of a sudden, it'll shoot back towards South America. There it is. That's El Nino. And it brings all this warm water here that makes the air warmer through here and gives us warmer weather in the winter, kind of like we've had this year. Alright, here's another idea. This one, you see El Nino's coming in here, it repeats itself. It shows you the winds blow it back, blows it this way, that warm water builds up out here in the Pacific, it's about to build up here, and then it rolls this way towards South America, bringing all that warm, wet weather to us.
phenomenon called elnino disrupt weather patterns around the world. In 1998, it caused devastating floods and mudslides in California. Around the same time, it also caused these floods across the South. But it all started thousands of miles from either location. Picture the equatorial Pacific. That's South Asia and Australia on the left, and South America on the right. Pacific trade winds normally blow from east to west, pushing warm surface water with them. The warm water evaporates, adding moisture to the air, bringing the annual monsoons to the region. In the eastern Pacific, as the surface water is pushed westward, cold water wells up from the deep to replace it. The cold water helps keep the air and the South American coast dry. But sometimes the trade winds stop. Scientists don't know precisely why. When they do, the warm water moves back east. That's when El Nino takes hold. The pattern of rainfall is reversed. Australia and South Asia suffer drought, and coastal South America is hit by storms. But the warm water in the eastern Pacific causes other changes as well. High atmosphere wind is called jet streams circling the planet. El Nino can alter the path of those winds, driving Pacific storms to California. As the jet stream winds continue across the continent, they can keep the colder Arctic temperatures at bay. That can make for a warmer winter in the northeast and northwest. That's why in 2010, when El Nino once again brought flooding to California, farther up the west coast of Vancouver, the Winter Olympics were hampered by unusually warm weather. It was all thanks to El Nino.
Now, the opposite of El Nino is La Nina. La Nina is when the wind is blowing the water out, and El Nino is when the water overcomes the wind and rolls back towards South America. Here's South America, here's South America. You can see the difference in the two. I want to talk now about deep ocean currents. Deep ocean currents are caused by density. They're also known as density currents, and they happen below the surface of the ocean. And that's when water becomes denser. Well, how can water become denser than other water around it? Well, there's two different ways, okay? And that is the density of ocean water based on its temperature and on its salinity, the amount of salt that it has. This is on page 122 in your books. I encourage you to look at that. We're going to go to this link from NASA right here. It kind of explains what's happening here. Okay, if you'll follow this, this is a surface current. It's actually the Gulf Stream. It comes up through here, and when it gets up here, the water gets so cold, it actually sinks. And when it sinks, it goes down, and you can see it turning right here, sinking, and it actually heads back towards the equator. So here, it's coming back towards the equator. And it actually goes down all the way to the poles. Past Africa, and as it comes up here, right in this area, right in here off the coast of Australia, because of the terrain, that sort of pushes it back up and it starts to resurface. Okay, this water is very cold now because it hasn't been near the surface of the as I said, temperature also affects the density of water. We're going to go to a good link here. Let's hope that it works this time. Alright, if you're watching this, you can see the red is warm water. It's rising to the top. The blue is very cold water. It's sinking to the bottom. This will cause deep ocean currents. Colder water is, the more it'll sink. Okay, thermocline. Cold water is denser than warm water. When water near the poles cools, it becomes denser and sinks below the surface of the ocean, under the warm water arriving at the equator. Sets up what's known as the thermocline.
Hello, I'm Corey Champ. Today I'll be highlighting the density circulation apparatus used with pwer and SmartView software. The density
Okay, what he's going to do is he's going to show you the different densities of cold water and warm water.
circulation apparatus is new to Pasco, and today I will highlight its use in an earth science application, modeling the thermocline. The apparatus is two 1-liter plexiglass containers connected by two flow valves which allow water to flow between the chambers. Today's activity
We're going to
comes
skip
from
ahead.
the user's manual, which is supplied with the apparatus. Manual off.
Here he's pouring cold water into the left side. And here he's pouring warm water into the right side.
Okay. Now I've pre-configured the software to save some time.
Now he's going to talk a lot, so we're going to skip ahead to where he actually opens up the valves, which is kind of cool. He's showing you the temperatures of the warm side and the cold side.
So there's clearly a difference in temperature between these two water bodies.
And now he's finally going to quit talking and open up the valves. You can see the cold water running in on the bottom, coming underneath, over here, underneath the cold water, and underneath the warm water. The warm water is coming through then and filling in on this side, and that's actually how deep ocean currents work. Cold water will come in. As warm water moves out, cold water will come in to replace it.
There's a smooth, continuous flow as the water bodies.
Okay. Now, the halocline. What the heck's that? As water freezes in the Arctic, it leaves behind salt because salt does not freeze. This mixes with the ocean water, making its salinity greater. In other words, the ocean water becomes saltier because it didn't take the salt with it. As a halocline is an area where denser, saltier water sinks to the bottom of the ocean. So, here, new ice forms, and as it forms, it releases salt. Salt comes down here. This area becomes saltier, and this water sinks. Okay. Arctic Ocean has a distinctive feature called a halocline. It's a layer of cold salty water that acts as a barrier between sea ice and deeper warm water that could melt the ice. So what happens is this halocline, the cold saltier denser water forms because as the ice forms up here, this water becomes saltier. Alright, I'm about out of time. You guys have a good day. Please look at the other videos I posted here on Blackboard. Thank you.